Good morning, good afternoon, and good evening, everyone. Once again, this is Dr. Samuela Guida from the International Water Association, and welcome to the fourth day of the PrimeWater Multi-User Panel Stakeholders Week. Today, we focus on energy sector. So some housekeeping rules while we're waiting for the last people to join. If possible, please rename yourself with your name and your company. Please feel free to introduce yourself in the chat, say where are you calling from. And please note that the meeting will be recorded and posted on the PrimeWater YouTube channel. And so if you have any concern about this, please contact me. There is my email address. If possible, share your video, but as you wish, but please mute your microphone where you're not speaking. And for each presentation, you'll see down a chat box. If you can please add your questions there, and they do indicate the person you are addressing. And finally, note that after the meeting, you will receive an email with the slides and the recording of the session. So as I was saying, this is the PrimeWater Multi-User Panel Stakeholder Week. So what is the multi-user panel? So PrimeWater is an European project, and we have a multi-user panel, a group of experts that serves as an international panel of users that provide feedback on Earth observation-enabled services that are developed or extended in the context of the PrimeWater project. So the multi-user panel participates also in the co-generation process itself through dialogue like the one that we are having today. The first multi-user panel meeting was held in October 2020 as a workshop, and in that occasion we gathered initial feedback on what different users think about different services. And this year, the second multi-user panel, we are organizing it as a stakeholders week. We started on the 15th with a session on water resource management. Then we had a session on disaster risk management. Yesterday, we have a really interesting discussion about potable water. Today is energy, and tomorrow is the amenity, recreation, and aquaculture. And all the links to join each of these sessions are in our website, and the recording, as I was saying, is in the YouTube channel. So the main objective of this week's events will be to provide an overview and an update on the services that PrimeWater can offer to all of you, understand how different sectors are using Earth observation services to address issues such as extreme hydrological events and the harmful algal bloom. And finally, we want to discuss with you the added value of PrimeWater products when addressing these issues. So today we have a really packed and nice agenda. We have an initial session about the introduction of PrimeWater, and Elias here will talk about the state of the art on hydrological forecasting for the hydropower sector. Then we will have a presentation and a moderated panel discussion, and we will finish with a serious game. So Elias, the floor is yours. I'll share the screen now.
Thank you, Samuela, and good morning, good afternoon, and good evening to all the participants. Great. Okay, so it's actually very nice for me to start this presentation with state-of-the-art hydrological forecasting, which is something that we've been setting up specifically from the PrimeWater project. And it is very important to communicate to all the participants that this hydrological forecasting service is actually a state-of-the-art service using knowledge that we have in-house at SMHI. And also not only technical and operational knowledge, but also scientific knowledge. So we try to provide a very much tailored service and Yes, indeed, at the edges, at the frontiers of hydrological science also. And why we are focusing on the hydropower sector within PrimeWater, this is simply because the hydropower is the world's largest source of renewable energy. And there's been actually unused potential to be explored, especially in these times that we are having a global energy policy that is changing. Only in 2017, there's been 48 billion US dollars that have been invested in hydropower project, and that indicates the importance of the sector. But the hydropower is not an easy kind of like sector. It is the operational rules are complex, and then one has to take a lot of different variables into account, including also the environmental uses. One needs to handle the peaks demands of electricity, and of course that has to contribute to the supply-demand balance. And at the end of the day, the decisions are actually weather and climate and hydrologically dependent decisions. So one has to take into account the variability of this complex interaction between weather, climate, and hydrology. And decision making, this is done at different time horizons. So the operators are focusing on the short-term decision making, which is actually 2 days into the future or 1 day into the future. But there are also other type of decisions that are more on the monthly time horizon to the future. And last but not least is actually the decisions that the managers take with information that goes beyond the 6 months into the future, like for instance, the reservoir management and the optimization, planning and maintenance of the reservoir. So one has to take directions there, which is like cost and benefit of the transparency, the multi-objective optimization of the system, and of course, the resilience to climate change. Climate change is an important factor that cannot be neglected when decisions are actually made. Within the PrimeWater, we are focusing on two type of time horizons into the future, or in a better way, two different numerical weather prediction systems that allows us to go up to 10 days into the future with specific information, and also with a seasonal forecast that allows us to go 6 months into the future, or even depending on the method, we can go up to 12 months into the future. And of course, depending on the forecasting horizon or the system that is used for making this forecast, we can address the short-term and also the long-term decision making. But we know from practice, we know from science that depending on the system, the further we go into the future, the more reliable the forecasts are from the meteorological side. But this uncertainty, the meteorological uncertainty, is also propagated to the hydrological forecasts. So this is kind of like schematically how the forecasting skill is dropping as a function of lead time. So like the forecasting lead time. Nevertheless, we have been doing science on trying to bring the skill up, even when we are focusing on longer lead times, and this is what we are disseminating in the service. Now, from the hydrological setup of the service, we have based the operational systems to a hydrological model, which is the HYPE, which is a semi-distributed process-based hydrological model, allows us to represent the processes above the ground, land routines, river and lakes, and so on, but also takes into account water management. So, for instance, if there's irrigation, or if there is a reservoir regulation at the river system, then we are able to represent these processes as well. And it is the setup of the model has been done for the entire globe. And this is the model called Worldwide HYPE for us. And within the PrimeWater, since we are focusing on specific regions in the US, Australia, and in Europe, we have been taking this global model, and we have been extracting the domains of interest and we have been trying to evolve the hydrological service and the model outputs specifically for these regions of interest. And how we have been doing that, this is part of the service evolution. So firstly, we have been recalibrating the model parameters, redelineating the system and recalibrating the model parameters. And secondly, we have been working with data simulation of Earth observations and also in situ data. And at the end of the day, we are able to provide a service that allows us to predict, to model and forecast not only water quality, water quantity variables, like for instance, river discharge or inflows in the reservoir, but also water quality parameters like nitrogen, phosphorus, and sediments, which are all very much important for the hydropower sector. Now, let me take you to the work being done with the recalibration of the parameters. We focus on the science that has been accumulating, the scientific knowledge that has been accumulating at SMHI. So there we have been using multi-objective optimization algorithms to define the model parameters. But the most important here is the fact that we are not focusing the model optimization towards discharge only, because at the end of the day, discharge is not the most important variable. There are also other important variables that one has to model. So we have been taking advantages of Earth observations. Here, there's some examples of actual evapotranspiration and potential evapotranspiration, and also the river discharge. So we have been optimizing the model parameters in order to respect all these different variables. And this is a very powerful optimization method, because we are able to not overtune the model parameters to a single variable, but we are able to have the right model for the right reasons. The final conclusion here is that we managed to, through this optimization and recalibration exercise, to improve the model performance. Here, the model performance is quantified with an asset cliff efficiency that has an optimum value to 1. So the performance jumped from 0.25 to something close to 0.75, which is a very significant increase in the model performance. And of course, this is very much encouraging, because it is a way to disseminate the trust that we have in the model outputs. The other type of service evolution came from data simulation, and this is a hot topic in hydrological community. We have been doing a lot of science there on how which variables we should assimilate and when we should assimilate these variables. So we've been focusing on a scientific case study in a river system which is heavily regulated for hydropower purposes, and this is in north of Sweden. The hydrological response is very much seasonal, with during the spring and the summer having the snow melting, which is actually depicted here with this with the red line. So we have the spring floods during the months of May until July or August. And this is an outcome from snow melting with also precipitation. So here we focus on this river system, and we have Earth observations downloaded coming from the European Space Agency and also from NASA. We have snow water equivalent, fractional snow cover, actual evapotranspiration and potential evapotranspiration, but also the hydropower companies provided to us river discharge and also reservoir inflows. So we had 4 variables coming from Earth observations and 2 variables as in situ data. And we have been working in a previous investigation with my colleagues on doing data simulation of these variables for improving the hydrological model outputs. But there was no forecasting in this investigation. We quantified the added value from the data simulation, but we were not able to quantify the added value in the hydrological forecast. And this is what we did actually within the context of PrimeWater. This is only one example, one figure of the many figures we produced in this investigation. But what I want to communicate is the fact that whenever we assimilated either Earth observations or in situ data, it improved the hydrological forecast in the first week for sure. And these are the results for the different seasons, winter until autumn, as you can see here. This is a metric, again, the CRPSS that is optimum to 1. So we want these box plots to go as close to 1 as possible. The conclusion here is that depending on the season we are focusing, the assimilation of the product plays a different role. So for instance, we see here the importance of the snow products in the spring, simply because spring is a very sensitive period for hydrological forecasting with an interplay between snow accumulation and snow melting. So it's very important for us to quantify the snowpack. And this is where the models, the hydrological models, are usually lacking of representing. So assimilation of these variables had a significant impact to the hydrological forecast. And this is, again, is very important for the hydropower sector, because indeed it quantifies the added value for them for decision making. Here, there are a couple of examples, one again from Sweden, and in the next slide it will be from Spain, quantifying how much important is this data simulation in terms of economical benefit. So we are not communicating to the hydropower companies the added value in terms of how much water can be saved in the reservoir, but we are communicating the impact, like how much money they can benefit from doing this type of hydrological forecasting with data simulation. And we concluded that for the case of Sweden, the hydropower companies could save up to 1 million euros per year, which is a very much significant value for them. It's coming now. For the case study in Júcar River system in Spain, there we did not see significant benefits in terms of economy when it comes from the hydropower sector, but since the Júcar River system is a very complex one with a strong nexus between the different sectors, specifically here it is the hydropower sector and the agricultural sector, we concluded that, or the results show that although the economical impact for hydropower is not that significant, there is still, because of the dependencies between the sectors, there is still significant impact for the agriculture. So by doing better hydrological forecasting, the hydropower company has small benefit, but the agricultural sector is going to have a much stronger benefit there. And with that, I want to stop. Thanks, everybody, and I can take questions at the end of session 1.
Thank you, Elias. And if you have any question from Elias, please do not hesitate to write them in the chat. We now have a presentation about the PrimeWater operational platform.
Hello, I'm Vangelis Romas from Envis, and I'm going to make a short presentation of PrimeWater's operational platform. The platform is available through a web browser, either through the PrimeWater's website or directly through the second link. This is the initial page of the platform with the 4 operational case studies of PrimeWater in Europe, United States, and Australia. The PrimeWater currently offers 4 services, which are the EO-based monitoring system, the hydrological forecasting service, and the water quality forecasting service, which is offered both by process-based and data-driven models. I will now jump to Melbourne Western Water Treatment Plant, and I will start with the EO monitoring service. which provides operational EO-based water quality products from Landsat and Sentinel missions. On the map here, we are able to see the latest available satellite image for our case study, which is for today, obtained just a few hours ago. The product shown here is chlorophyll A concentration at a resolution of 10 by 10 square meters, and by clicking on the map, we can read chlorophyll concentration at various points of interest. You may notice a gap here in the center of the map, which, as you can see in the true color image, is due to the cloud coverage. Apart from chlorophyll A, we are also able to quantify turbidity, total suspended matter, total absorption, shaking disk depth, and also a harmful algae bloom indicator, which classifies the probability of hub existence based on the presence of phycokianine pigments. Also, we are able to provide surface water temperature from Landsat. However, this product is not available in this case study due to the low resolution of Landsat at 30 by 30 square meters and the small size of the ponds, which causes a strong interference with the land boundary. However, surface water temperature is available on all the other case studies. In the calendar here, we can see the dates with available overpasses of satellites, and we can go back in time until 2015. Also, there is a useful tool for exploring the temporal variation of a parameter in a selected area. For example, in the graph here, we can see the historical turbidity values for the last 3 years at the selected point of interest. Currently, these EO-based water quality products are produced by EOMAPS processing algorithms. We also aspire to include algorithms from other remote sensing partners of PrimeWater, for example, CSIRO's processing algorithms. And we also aspire to include hyperspectral water quality products from Prisma and DESIS missions, although these products will not be available operationally, but only for historical periods. The next functionality of the platform is the hydrological forecasting service. I will now jump to Lake Hume and select the Hydrology tab. This service is provided by SMHI and the worldwide HYPE model setup. In the map, we can see Lake Hume and all its upstream hydrological catchments. These two contribute directly in the lake, and if I click in one of them, I can view the hydrological forecast for 10 days ahead regarding river discharges entering the reservoir. In the graph here, we can see hintcast and forecasted values of river discharge for today and the following 10 days. Apart from river discharges, the hydrological model provides also forecasts of nutrients, nitrogen and phosphorus, and suspended sediments. And those variables are a very important input for the water quality modeling that is performed inside the reservoir. The hydrological model offers both a deterministic and probabilistic short-term forecast. If I switch to the probabilistic forecast, then we still have 10 days forecast, but this time we simulate a hydrological ensemble of 51 individual model trajectories, as you may see in the graph. So, apart from the average ensemble value, we can have an estimation of possible range of values for each day, and we can calculate some useful statistics such as percentiles, which is a valuable input for quantifying and dealing with forecast uncertainty. There is also a third hydrological setup, which is available only in the European case study, which is a seasonal hydrological forecast, where we can have forecasts for up to 7 months ahead, averaged on a weekly basis. Moving further down to the modeling chain, we have reservoir water quality forecasting provided by ENVIS. This is the Moulargea reservoir in Sardinia, where we have used the Dell 3D suite to set up a 3-dimensional hydrodynamic model coupled to an ecological model. The hydrodynamic model is forced with meteorological and hydrological input and provides us the circulation pattern inside the reservoir and water temperature for the next 7 days. The map currently displays water temperature for the top layer on a grid of 100 by 100 square meters and 20 vertical layers. By clicking on the map, we can read temperatures at each cell. We can also visualize the water velocities with these nice animated arrow traces, and of course I can move this time slider up to 7 days ahead in the future in 6 hours intervals. Actually, there is a nice tool that visualizes the evolution of the parameter in the forecasting period. For example, in the graph, we are now observing the diurnal variation of temperature in the topmost layer. As I said, we are using a three-dimensional model, so apart from the top layer, we are also able to get information for any depth we would like. For example, here, in the middle layer of the reservoir, the temperature variation is not so pronounced. Values are almost identical for the forecasting period. The vertical profile of each forecasted parameter can also be viewed in a separate graph for any selected point. For example, here the model indicates that there is a thermal stratification at the selected point of the reservoir. The parameters of the water quality model include chlorophyll A, nutrients, phosphorus and nitrogen, suspended sediment and dissolved oxygen. Here I have selected chlorophyll A, and the map and the graphs are now showing chlorophyll concentration. And finally, there is a third tool that allows us to view cross-section of any simulated parameter along the two main directions of the reservoir. Both in the hydrodynamic and water quality models, we are incorporating data simulation techniques that are using satellite-based products as well as in situ measurements to correct the model state and avoid error accumulation. So with the process-based models, we are able to expand the available information that we have for our reservoirs up to 7 days ahead in the future. And compared to the Earth observation, we can also have information at deeper layers and information about non-optically active parameters like nutrients. Apart from the process-based models, ENVIS is also employing machine learning models for forecasting chlorophyll and algae bloom events. So I will now move to our last case study, which is Lake Harsha. Data-driven models are trained for specific areas of interest presented as triangles in the map using meteorological forcing, forecasted nutrient fluxes from the hydrological model, and are compared against EO-based chlorophyll values or even in situ measurements, since in Lake Harsha we had some nice historical time series with a large number of chlorophyll values and cyanobacteria cell counts. We are currently using three types of machine learning algorithms: Gaussian process regression, random forest, and random undersampling boosting. I will stay in the GPR model, which predicts chlorophyll A concentration only in the surface layer this time. By clicking on a point of interest, we are able to read the chlorophyll values at the current time step. Again, there is a graph that presents the time variation of the forecasted parameter. The dashed line are the hindcasted values, the continuous line are the chlorophyll values for today and the next 10 days ahead. One nice feature of the machine learning algorithms is that they can provide us with some confidence levels. So for an 80% confidence level, we can see that the predicted values of chlorophyll A concentration increase from 4 micrograms per liter to almost 20, and even higher for the 90% confidence interval. I will now jump to the random undersampling boosting algorithm to present you a different type of product we are using for bloom forecasting. So this algorithm has been trained to predict cyanobacteria cell counts, but not as a scalar quantity, but as a probability of exceedance of a specific threshold specified by WHO. And we have made this choice because we have seen that the model has a stronger skill in predicting if cyanobacteria concentration are going to be over or under the threshold of 100,000 cells per ml, rather than in quantifying exact values of cell densities. So in the graph we can see that the model predicts that for the selected point of interest and the entire forecasting horizon of 10 days, we're having a no-hub situation with a high confidence level. While if I click to this point, then we see that we still have a no-hub situation, but this time with a lower model confidence.
Perfect. Thank you, Evangelos. Thank you, Elias, again. If you have any questions, once again, please do not hesitate to ask them in the chat. I'll open the floor for some questions, and maybe I can start by asking a question to Ilias. So Ilias, in your presentation, you mentioned that in the PrimeWater service, you provide forecast 10 days ahead and 7 months ahead. So I was wondering, why not using sub-seasonal forecasts to better predict the period of 1 month ahead?
Yeah. Thank you, Samuela. I think it's a good point for service evolution, actually. Traditionally, I think we have to see the benchmark of a service that the hydropower companies are operating. So traditionally, they are using medium range forecasts, so the things that we provide, which is 10 days into the future. And I think our services is evolved from the perspective of like us providing both deterministic and probabilistic forecasts to them, so they can have a range and understanding of the uncertainty of what is coming into the future. And then we go to the other time horizon, which is the seasonal forecast with 7 months into the future information. But indeed, we are just missing something in between, which is the new type of climate models that allows us to predict, to have information at the sub-seasonal range, which is a month into the future or a month and a half into the future. So I think that if we have to evolve our PrimeWater services, then we could introduce this type of forecast as well. And as I saw it in one of my slides, the decision making from the hydropower companies is done like 2 days ahead, 2 weeks ahead, and then 6 months ahead. And we could, with this sub-seasonal forecast, we could address better this type of information needed for 2 weeks decision making. And I think, well, at SMHI, we have the knowledge because we've been working with sub-seasonal forecasts. We have been doing that for the entire pan-European domain. It is a matter of customizing this type of service within the PrimeWater context. And yeah, I think I see it more like a step 2, like for service evolution. Yeah.
Sure, thank you. And one question for Evangelos. So what type of data sets are required for the setup of the water quality forecasting services using the 3-dimensional reservoir models?
Okay, thanks, Samuela. Well, we are using for the reservoir modeling 2 distinct models, the hydrodynamic one and the water quality one, coupled to the one to each other. For the hydrodynamic model, we need meteorological forcing, so air temperature, cloudiness, humidity, and winds. For the heat balance, and river discharges and outflows for the water balance. Meteorological forecasting is provided by NOAA's global forecasting system, which gives for any point of the globe at a resolution of 0.25 degrees these parameters. And but we're also able to connect to other meteorological service providers like ECMWFs. And for river discharges, we are using the hydrological forecasting provided by SMHI, either the European setup or the worldwide setup, depending on the case study. Now, when it comes to water quality modeling, here we need again meteorological forcing, this time for the growth processes of the algal species in the reservoir, and the nutrient fluxes, which are again provided from the hydrological forecasting. Additionally, for the calibration of these models, we need some water quality measurements inside the reservoir for a historical period of 2 to 3 years, preferably. And this can be provided either by EO-based water quality products or by in-situ measurements, monitoring campaigns, etc. And in PrimeWater case studies, we are using both of these sources. EO-based water quality products are available through EOMAP's processing algorithm from Landsat and Sentinel. And we are also using in situ measurements from the reservoir owners. And also, if these water quality measurements, apart from the historical period, if these can be available operationally in real time, then, as I mentioned, we can use them for correcting the model state using some data simulation techniques.
Thank you, Evangelos. Ilias, another question for you. So how easy would it be to set up the hydrological service at other domains of the world?
Yes, I think one of the good things we did in PrimeWater is that we took advantage of the worldwide hype hydrological model, and there's been a lot of effort from our group on setting up this model and the service. Like the challenge is there mainly to calibrate the parameters and also to take into account human impacts and so on. But nevertheless, what the users need is actually good information at the local scale, and so now I think we have kind of like a framework that allows us to customize the worldwide hype service to the local conditions that the users are operating. So by customization, I mean that we take the model, we make the extraction, then we could do redelineation to the special resolution that the users are interested to get information from the model. And then we could recalibrate the parameters with the same kind of like framework that I presented earlier, and then run it in a service line that at the daily kind of like mode provides information to the platform. So I think that since the model service exists for the whole globe, having applications at other domains around the world is kind of like straightforward. It's a matter of a few weeks of work and then it's done. So we are not dependent on setting up something new from the beginning, because it is we take advantage of something that exists already.
All right. Thank you. I think we have time for another question for Evangelos. So if I have for a reservoir weekly sample for water quality parameter for a period of 2 years, would that be enough for training a machine learning model?
Hi, Samuela. This is Kyriakos speaking. I could take this answer. So you said weekly samples of, let's say, a 2-year-long period, correct?
Yes.
Well, the answer is that this is unlikely to be sufficient. To give you an idea of how we deal with it, practically, of course, as all data-driven problems, data adequacy actually depends on the scale, the complexity, and the dimensions of the problem. So since we're talking about phytoplankton dynamics, this can be highly nonlinear and complex and a multi-dimensional problem to simulate. So having such large data set, which practically translates into 100, let's say, of available data, I would say that it's highly unlikely to be sufficient. At least from our experience, one should look into greater periods of available measurements. And perhaps if I want to give you a rule of thumb, let's say, of the data size to be adequate, I would say that it should be in between 150 to 200 available measurements. So if we want to focus on satellite-derived information, this, let's say, 200, images to be processed correspond typically to 5 to 6 year long periods of time. considering all the issues, cloud contamination, revisit time of satellites, and so on. So to sum up, I would say that such small data sets would not allow for a credible development for a data-oriented model.
Mm-hmm.
I would say again that at least 200 observational data should be considered, which in terms of satellite-derived information, this can go up to 5 to 6 year long historical time series.
Okay, interesting. All right, so I think that concludes session 1. Thank you again to both of you for your very interesting presentation. And to the attendees, if you still have any questions, please do not hesitate to put them in the chat. I think we now go to a mini break. So just 5 minutes. It's 8:43 in UK. So we come back at 8:48. That's okay for all of you. So go grab a coffee and we'll see you back in 5 minutes. Thank you. Okay, everyone. I hope you're back from the break. We now move to session 2 of today. For this, I'll leave the floor to Catherine Cross from IWA, who will moderate the session. Catherine?
Thanks, Samuela, and thanks for joining for this second session today. So yeah, I'm Catherine. I work for IWA as a consultant. I'm based in Bangkok, Thailand. So we have our speaker today is Cristina Diaz-Santos with Open Hydro. Cristina is a water resource and hydropower specialist, and her interest lies at the interface between academia and industry. By building and sharing knowledge to develop water infrastructure across the world. She's worked extensively across different organizations, including with developing good practices with multilateral development banks and advising international organizations on issues related to water in the hydropower sector. So I would like to welcome Cristina, and we look forward to hearing your views and perspectives today.
Thank you so much. Good morning, afternoon, evening, everyone. It's a real pleasure to be here. And what I would like to do is just cover a bit the spectrum of the challenges and opportunities with regards of improved Earth observation data and what that means into the planning and operation of hydropower plants. So I would like to start by giving an introduction of the present situation of hydropower globally. So by the end of 2020, we had over 1.3 terawatts of hydropower installed capacity. And as we see in the image to the left, China has the biggest proportion, and that's followed by Brazil, United States, Canada, India, Japan, and Russia. This represents about a growth of 1.6% from 2019, with a total added capacity of 21 gigawatts. Where nearly 2/3 of the growth came from China. And this 1.6% will have an implication of what we explain later, what is expected to grow for the sector. This also represents, as Elias introduced earlier, about 16% of the shared total electricity generation globally, as we see on the picture to the top right, where hydropower represents more than half of the renewable electricity generation. And I would take a look at the bottom right graph. We see that the share varies from different countries. So there is a bit of a difference between the emerging and developing countries and advanced economies. In the case of emerging and developing countries, the share is more polarized, and we see that there are more than 30 countries where hydropower represents less than 10%, and almost 30 countries that represent almost 35%. Although when we look at the share in global final consumption, it's much lower. And this has a lot to do with the level of penetration of variable renewable energy in the energy mix of the different countries. And as we will see later, this picture will change significantly over the next decades in order to reach the net zero target. So looking now at the present and the future. So we see here is that hydropower has an aging fleet. In this graph and study done by IEA, we see that in places like China, Latin America, and Asia, most of the hydropower assets are more than 40 years old. If we look at the entire capacity globally, more than half is more than 30 years old. And there's an estimation that by 2030, over 1/3 of the existing capacity will have undergone or will be due to for modernization. And the modernization is an important factor because the performance and reliability of the components are reduced as the station ages, impacting output, revenue, and safety. And there is also a great opportunity to use modernization to deliver co-benefits, such as providing greater flexibility services to support variable renewable energy penetration, addressing environmental impacts and social legacy issues, and building climate resilience. And this has a lot to do with what is expected in the roadmap of hydropower and other renewables in the years ahead towards 2050. So looking at what is coming ahead, hydropower assets have truly a transformational role in addressing the challenges that we have related to climate change, water, and energy access. And as we see here, according to IRENA and IEA, hydropower capacity needs to double to achieve the net zero pathway by 2050. And it estimates that the average annual investment will need to increase by almost fourfold. And now it's important to keep in mind this picture where we see the important surge of wind and solar, and in comparison with what is expected for hydropower, because that has also a lot of implications on what is expected from the investment. First of all, because not all capacity added will come from new hydropower assets, and because innovative solutions will be required to provide the flexibility that the system requires. And in that sense, improved Earth observation data and forecasting plays a key role in this aspect. So if we take a look more closely of, in general, what are the challenges and opportunities that we have ahead. First of all, in terms of flexibility and storage, as I was mentioning, because with the higher penetration of variable renewable energies, the hydropower flexibility role is becoming more prominent. And moreover, due to climate change and the hydrological vulnerability, we're going to see more extreme events that are going to make more challenging to provide the storage capacity, both for water and energy purposes that our society would require. So more and better data would be required to provide, for instance, smart modeling and control solutions to increase the flexibility of the asset, but also the flexibility at the unit level and the operating ranges. And second of all, in terms of digitalization, so we've already seen that more than 1/3 of the hydropower capacity is expected to go under refurbishment or modernization by 2030. And it's estimated that about 42 terawatt-hour generation could be added to the present hydropower production just by implementing digitalization. And thirdly, in terms of requirements for climate reporting, global initiatives and frameworks that have emerged to urgently improve and scale up the disclosure of climate-related information. As such, we have the Task Force for Climate-Related Financial Disclosure Recommendations, the EU Taxonomy, the Climate Disclosure Standard Boards. And in that regard, Open Hydro estimates that there would be more than 1 gigawatt of hydropower capacity that would be expected to disclose climate-related information over the next 5 years. If we look more closely into hydropower storage, so we see that reservoir storage is required to regulate the fluctuation of the natural river flow, and that helps to ensure a reliable water supply, of course, power and flood control services. But as hydrological variability and sediment yield increase due to climate change, the need for adequate reservoir storage will increase, apart from the demands imposed by just our growing society. So if we look at the graph on the left, estimates indicate that the net global volume of reservoirs is reducing at a faster rate than we are adding through the construction of new dams. As we see, the per capita storage is now estimated to resemble conditions that last experienced in the 1960s, and continues to trend downwards. And if we look at the graph to the right, we see that increased sediment yields due to climate change will further exacerbate the conditions. if reservoir sedimentation is not effectively managed. And moreover, in terms of hydropower energy production, it's estimated that it's been reduced annually at the global rate of 1% due to the loss of reservoir storage capacity and damage to electromechanical equipment caused by sedimentation. So as such, it will be even more relevant Earth observation data to, first of all, help identify baseline and seasonal trends for sediment, and to monitor the sediment dynamics, calculate the sedimentation flow and rates, and of course also in terms of water quality, the environmental monitoring of the algal bloom evolution in the reservoir. In terms of flexibility, so when we talk about flexibility, previously we've talked about more of the water perspective, now looking at the energy perspective of the storage. Flexibility here refers to the ability of the power system to respond to load changes just by adjusting its sources. So for hydropower, the main source of flexibility is the variation of the water levels in the reservoir. Also the ability to shut down or start generating a unit at a really short notice. And of course, also the ability to spill water. And given the high penetration of variable renewable energy, wind and solar, that we require to reach to the net zero targets, it becomes really invaluable the characteristics of hydropower to provide flexibility to the system, both from the short-term stability, but also to the long-term seasonal storage. So rather than, what we present here is, rather than just looking at the specific shares of wind and solar deployment and what that might imply, we are showing the phases framework that was defined by the International Energy Agency with a typical sequence of what would be the challenges that the system would face as more and more variable renewable energy sources are connected into the grid. And then we see into each phase the requirements that could and what could be the role that hydropower plays. And basically what we say is that it can play a role from the really short need of forecasting of days to a long forecasting of months and years. In the phase one, where there is a need for additional short flexibility, hydropower can provide that additional short-term variation into the power system. And the phase two, where the ability to quickly ramp up and start at any time, including switching between producing and consuming energy, might provide an advantage to hydropower over other conventional energy sources such as thermal. But in that case, we have that's the advantage of the technology, and the challenge is to be able to have the proper data to do those forecasting. And the same thing goes for the phase three, where we are looking at more, not only just the short and medium-term flexibility, but also the long-term flexibility becomes very important, because then we are in systems that are very dependent on water variability. And also in the final phases 4 and 5, hydropower can provide the substantial amounts of both the capacity, so the power driven short-term flexibility, and the capacity plus energy-driven medium-term and long-term flexibility. In terms of opportunities for digitalization, collecting and processing real-world data to adjust the actual working conditions of hydropower turbines can provide advanced grid supporting services without compromising the station's reliability and safety. So digitalization and innovative technologies can be applied to satisfy several high-level objectives throughout the entire life cycle of the hydropower asset, as we see in the image that applies to safety, so the integrity of dams, the integrity of the hydropower system and equipment, but also very important, all sustainability aspects, so such as water levels, ecological flows, climate change impact, water quality, fish management, sediment management, and also from the economic and commercial perspective, both from the short-term operation plans and the long-term strategic investment decisions. And these include more efficient operating and maintenance of the hydropower plants. And as such, it's actually estimated, as I mentioned before, that we could even have 42 terawatt-hour of generation added to the system that we have right now, just by applying digitalization. We see that the aging of the hydropower fleet, the hydropower fleet is aging, as we mentioned before, and that doesn't only have implications for modernization and digitalization. In most countries in Europe, the US, part of Latin America, the licenses and permitting options of operating hydropower assets are coming to an end. And over this next decade, governments will have the task to review the existing licenses, assess the risk and opportunities, define the new needs for those reservoirs, and decide what licenses would be renewed and under which criteria. This is just an example of a study done in Europe where we see that most countries are already in that process, such as Italy, Greece, Spain, France, and we see Great Britain and Austria coming ahead. And that has significant implications for the longer forecasting or what is expected in the longer term, but also the day-to-day operations of the hydropower assets once those we see how are going to be the new licenses. And also from, as I mentioned before, from the perspective of the climate reporting requirements, we've mentioned the global initiatives that are coming up to help scale up, improve climate reporting, climate information reporting. And as we see at Open Hydro, the hydropower capacity in the countries that are working towards mandatory requirements, so enforcing the TCFD recommendations, is about 500 gigawatts, and that represents nowadays about 34% of the hydropower capacity globally. But now, if we look at and probably it might happen rather sooner than later, if the G20 countries reach an agreement to enforce TCFD recommendations, this hydropower capacity that will be subject to disclose climate-related information will increase to 1.2 gigawatts, so roughly about 80% of the world hydropower capacity. And this has big implications into translating the physical risk of hydropower assets into to the corporate level. And just finally, and to summarize here, like what we see of the present and future of the hydropower sector, so that we see the capacity will have to double by 2050, but the investment might need to multiply by 4 compared to what is happening nowadays, because we know we have an aging fleet and there is also necessary new hydropower, but then there will be changing requirements for permitting licensing on hydropower assets. And briefly about Open Hydro, we are an analysis and advisory international organization with expertise in climate change and policy in the hydropower sector. We provide data, knowledge, and analysis to answer most of the pressing issues within climate finance and the hydropower sector. One of the challenges to mobilize the capital that is needed for climate action is actually the gap between corporate level and project level disclosure, and this is a place where we aim to reach by empowering organizations to demonstrate the contributions to climate mitigation, resilience, and adaptation. And just before saying thank you to everyone, I would like to leave you just with our vision for a climate resilient zero carbon planet where water and energy are accessible to all. Thank you.
Thank you so much, Christina. That was a very inspiring and insightful presentation. I was very interested in a lot of what you had to say because I'm based in Bangkok and I was thinking about a lot of this in the Mekong context. So I think, well, now we're going to move to a panel discussion with yourself and Ilias. So Ilias, we could put on your camera. We have a few questions, but if anyone has also any questions that they would like to ask in relation to the presentation, please just put them in the chat. So the first question is, I was very taken with what you, Christina, what you were mentioning about how digitalization could provide this additional 42 terawatts of power. So how do you think new technology based on Earth observation specifically, and unmanned aerial vehicles can contribute to advancing the sector as part of this digitalization push?
Absolutely. So it will have great implications, and it would be essential, both from the water and the energy aspects. From the water, we see also with climate change and becoming more vulnerable to the climate variability, it's absolutely important to have a good forecasting and therefore be able to rely on Earth observation data to be able to manage what is required from the reservoir, not only from the perspective of what is needed for hydropower from the energy perspective, but also for all of the other uses. So it could be irrigation, water supply, but also from the environmental perspectives. So what we see now is that we have actually the opportunity now that we can go into digitalize and improve the systems that we have to look at what are actually the impacts of those assets into the system and into the basin, and how we can improve through improve operations and improve decision making. And for that is essential all of the data that you can provide. And also from the energy perspective, because so we see that we have a proven and a technology that we've been using for centuries. We have assets that have been operational for more than 50 years, and now they have the challenge to not reinvent, but be able to cope and provide the flexibility that is required by a system that now has much more variable renewable energy. So whereas then hydropower won't be only used for base load, but it would be necessary to provide energy when we don't have wind or solar. And for that, of course, and since that energy production depends on our water storage, basically that's the way the battery that we use. We really need that that data, as Elias was mentioning, not only the forecasting for the longer periods, but also the really short of days and even hours to be able to provide that.
Thank you. And Elias, what would be good to hear from your side for again, also looking at Earth observation and how it can contribute to improving hydropower production and management.
Yeah, thanks, Catherine. Maybe before that, I just want to say thanks to Christina, because her presentation was indeed very much inspiring. Now, regarding the answer to the question, I think that when you talk to the hydropower companies, they always say that they need observations. And in the past, the kind of like the standard practice for them was actually to install stations at different locations of the catchment, that they thought that this is kind of like they provide good information as a representation on average of the catchment system, or they used to go with let's say with snowmobiles and measure snow, or with helicopters and take these sophisticated instruments of taking like LiDAR images and so on. But now the technology, specifically of Earth observations and also the unmanned aerial vehicles, like for instance drones, is a new era. The Earth observations, the satellites have been very much sophisticated in terms of algorithms, and nowadays they do provide good information in space and time, something that in the past somehow had to be interpolated with mathematical algorithms, and also with the technology of drones, you could have kind of like good estimations with not much high cost, because you set the drone to fly and take some images and you analyze it later. So those things, those type of data, in addition to the new methodologies of machine learning that allows us to provide to filter errors or to improve the spatial resolution of the data coming from Earth observations or from drones, is definitely a new era for the sector. And you have seen in the presentations earlier today that the assimilation or integration of this type of observations and data in the modeling forecasting chain does give an added value. So I think that incorporating and integrating this type of technologies in decision making is definitely very much important for the sector.
Okay, thank you for that. And maybe just building on what you just said, a question again for both of you is on reliability of data. Again, this is very pertinent to the situation where I'm in the Mekong, where the Mekong River Commission has access to Earth observation data, but they need to have confirmation on reliability. So what are some methods to improve reliability or assist such agencies on making decisions with smaller uncertainty? Because that's always what it comes down to. So maybe Elias, you might want to start, and then Christina, it would be good to have your view on this as well.
I think reliability in the forecast has always been a challenge, and we have always in the scientific community discussing the fact that we have to communicate the reliability or the uncertainty coming in the data in the forecast. But I think one misconception is the fact that the sector itself or the operators, the managers, are aware of uncertainty, and they're making decisions using this uncertainty. So it's not a topic that they are kind of like lacking in terms of knowledge. I think that they are in a good state. Of course, that depends regionally, right? There are domains where the managers are good. They have good knowledge of reliability in the forecast, and other domains that they do not. Nevertheless, our task as service providers is to communicate this reliability. And indeed, there are methods of improving this by, for instance, initializing the service more frequently, because we saw the added value from frequent initialization of the forecast, or the discussion we had about introducing sub-seasonal forecast that allows us to improve the forecast reliability in the first month at least, and then making this extension towards seasonal forecast. So methodologies are still there. I mean, they are there, they have been developed. It's a matter of us as service purveyors to communicate the reliability of the service, and also for the decision makers to take into account the reliability of the forecast when they are making decisions.
Yeah. Definitely. That's an important thing to communicate. Christina, did you want to add anything to that?
Yeah, so from our perspective, it's true that we also see that reliability on forecasting is a challenge, and there are different, the needs through different regions are a little bit different. For example, so we look at the case of Europe, now with the common regulations, with the EU taxonomy, it's true that that becomes really significant, as companies, they need to provide data on their climate performance, like climate mitigation resilience, not only on their OPEX, so the operational assets, but also on the CAPEX, so what is coming ahead. And on that, that forecasting has real implications, because it has direct implications on their financial side. So that's one aspect, but then another aspect is also on regions where we see the need of developing new hydropower, or regions like Africa where we don't have so much in situ data, where then Earth observations is important to take a look at what that can offer, understanding, of course, and communicating well what is the reliability of that data. And in that case, it has a significant relevance, and is related to perhaps what you were mentioning with the Mekong, is to see what are the cumulative impacts when we are developing new assets and taking a look into the entire basin. And in that regards, and again, in places where we might not have that much data at the basin scale to do those assessments, Earth observation perhaps is a really good tool, together with the necessary capacity building to help bridge that gap in the regions where we need more hydro development.
Yeah, I think that's important to keep in mind. So I have a couple more questions, but I also invite anyone else online to just either type a question in the chat, or if you could raise your hand and or just unmute yourself and turn your camera on and ask a question. Please feel free to do so. Whilst we wait for any other further questions, I wanted to ask both of you. So Christina, you were talking about climate-related information in your presentation. So I wanted to ask you, firstly, how climate change is likely to affect the hydropower industry, and then also how climate services or climate forecasting, climate predictions can support, I guess, development of the hydropower industry. Like, how will that impact the hydropower industry? So climate change itself, but then also how predictions and models can inform operation and also development.
So yeah, climate change has a significant impact. So we've seen in the presentation from the perspective of sediment management and how that has a significant impact on how we operate the hydropower plants, but how much water we have available and how much storage we have available in terms of water and energy. And of course, in terms of managing extreme events, so flood and droughts, and coupling that with the requirements that we might have, or the new requirements that we might have for the operation of those hydropower assets that actually need to incorporate more flexibility into the system. So it's definitely an added challenge, climate change, besides what is required from the sector. So therefore, so good data to manage climate change and to provide informed decisions have a significant impact to improve the mitigation of climate, but also in terms of the resilience and adaptation. So we can see how this can help improve the resilience of each hydropower asset from the point of view of the safety of the infrastructure, of the quality and the sediment management and the flows of the water and the impacts downstream, but also in terms of the adaptation services that those assets can bring into the system. So, for example, looking into flood and drought control and those added services that the asset could bring into the system.
Okay, thank you for that. So Ilias, it would be good to also hear your perspective both on impacts of climate change and then how climate information can be used.
Yeah, thanks for this very interesting question. Always that climate change is a hot topic. I mean, for sure, we have seen that the impact of climate change in hydrology, of course, varies regionally, with more extreme events, either in terms of flooding or droughts occurring depending on where you are. But nevertheless, what is changing is actually the seasonality, like the intra-annual variability. And I think that for the case of the hydropower, especially the regions that the power generation depends on snow melting, there we have seen that the snow melting will take place earlier in the year. So that means that the sector needs to be prepared of these changes, and hence the regulation will be done differently within the seasons. Actually, last week I was in a meeting and I was a little bit surprised by one type of conclusion that stated that the climate change overall in the globe will not affect the generation of power from the hydropower sector, which was a little bit surprising. But then I thought that, yeah, maybe overall it will not change, but what it would be needed is actually the seasonal adaptation. So if the sector is adapted seasonally, maybe they will generate the power that they have at the end of the day or at the end of the year. So for sure, yeah, I mean, this would have been my feedback, is that it will require this monthly adaptation of the sector due to climate change.
Great. Thank you for that. So we have a couple of questions from other participants. So the first question, so I see Arnold, you have your hand up, but we have a first question, and then I'll pass over to you. So the first question is from Ekachukwu, and it's what effort is being made to partner with individuals or organizations, specifically in Africa, towards getting reliable data. So obviously not everyone has access or is using Earth observation on an operational basis. So how can there be efforts to improve access? So maybe Elias, you might want to touch on that, and Christina?
Yeah, sure. I mean, to me, data is a very much generic word. I mean, one could say, what type of data is it? Are we talking about local observations? Are we talking about Earth observations, or are we talking about forecasting data? Nevertheless, I think that the key point here in all type of data has to do with engagement with the local partners. We are simply because the knowledge exists with the local partners. So when we are setting up a service, we need, okay, local observation, thank you. The local knowledge is very much important. In the service implementation, we need to have this participatory approach, more agile approach on co-generating the service. And this is the case where such local observations could be part of the service, with fine-tuning of the service, tailoring of the service. Like, for instance, there could be bias adjustment of the meteorological forecast or the climate forecast towards the local observations. And then after that, we are having a product that is forcing the hydrological model to have some hydrological predictions. So the stronger the engagement is with the local partners, the more reliable the service will be, simply because we're integrating the local knowledge there. Okay, and I think great. we have been having that. I mean, depends on the African region. I mean, we have worked with the like with the Niger river basin there, with local partners and so on. So I think that is my experience towards the question.
Okay. Great, thanks. We just have a couple of minutes, so I'll let Arnold ask his question, and maybe Christina might want to reflect on that. Go ahead, Arnold.
Okay, thank you. Thank you very much. I'm Arnold Dekker from Australia. You said at a certain moment there's 1.3 terawatt of capacity installed globally, but you also said that 42 terawatt could be added by hydropower digitalization, which is effectively working smarter and with more prediction knowledge, etc. But I was I didn't understand the relation between the 42 terawatts and the 1.3 current capacity. Is the 42 terawatts that's added through digitalization, is that over 30 years, or how should I see that?
So yes, first of all, it's because we are comparing capacity and generation. So when we talk about 1.3 terawatts, that's the capacity in the system, and the 42 terawatt hour is what it could be generated. So that's why it's the different unit. So it is in a sense to show, I mean, that we actually don't have the precise numbers, but when we look at and that could be a really interesting exercise. So we know that we need to, so according to IEA IRENA, we might need to double the capacity, but how much of that is required to come from new hydro, and how much would actually come from digitalizing and modernizing the existing systems is a really interesting picture to put globally.
Great, thank you.
I did have another question, which is about determining new locations. I think Earth observation can play a role there, but I also think there will be a lot of resistance in new locations. At least in Australia, there's resistance against new locations for dams. So now we're getting a kind of contradiction, which is we're trying to increase hydropower because it's renewable energy, and we have to go to net zero, and at the same time there's environmental, let's say, focused opposition against new dams. Is this, how is this? And Earth observation might become enrolled in this, because obviously from Earth observation you can together with digital elevation model and all the modeling, you can find optimal spots, locations for new hydropower. So how does that conflict? How will that be managed?
If both of you can give your answer in 30 seconds, that would be good, because we've got to wrap up this session.
I think to me it's a matter of investment, and we have been doing that in Chile actually, but we have not used Earth observations because the Earth observations is observations of the past or the current status. I think for us, how we approach that is by doing hydrological projections, like how the hydrological systems are going to respond at the mid of the century or at the end of the century, and this is the information needed for them to make the final decision if they should make the investment for building a dam and so on. But then, of course, it's also very much political, right? I mean, we as service providers, we just tell them how future is going to look like. Now, for them to make the decision depends on many factors, I think.
Yeah,
Christina, any final words?
Yeah, so I would just say that it very much depends on which areas in the world we are talking about. Of course, there are places where most of the potential has been exploited, or at least what we would say the best sites for hydropower. So then, therefore, we might be looking at using the data to improve the operations of those assets, whereas in other regions, and that could be so Africa, part of Asia, there is still possibilities for adding new capacity, and there are still good sites that of course would need to have like the proper assessment, so we take into account all the possible impacts and how we can assess those, and for that Earth observation, local data and forecasting is essential.
Great, thank you both of you, and thank you everyone for the questions. I think we could continue have this discussion, and I'd like to definitely get your perspectives on how this would apply in the Mekong, but that's for another day. So thanks again. So I'll just pack back to Samuela, and we're going to have a break for a couple of minutes, and then we're going to have a game time.
All right, thank you, panelists, and thank you all the attendees. Yes, we'll have again 5 minutes break, so we'll be back in 5 minutes. Thank you. Okay, everyone. Thank you for being back. So I'll give the floor now to Ilias, who will moderate this third session where we will play the Call for Water series game. So Ilias, the floor is yours.
Thank you, Samuela. And yes, I think that now it's time for us to have a little bit of fun, simply because we are going to play a game. And but with this type of serious games is not only us to have an enjoyable time, but also this type of games are used for training the users. Users that have to take decisions based on forecast, and also training on the context of forecast reliability and uncertainty. So we have been developing this game within a previous Horizon 2020 project, and we have played the game with close to 500 users around the world. We have been analyzing results on that, because it's not only a matter of training the users, but also for us, the service providers, to understand what the users need in terms of reliability thresholds and uncertainty thresholds for them to make good decisions. So this is the Call for Water game, and I have already, something is missing, but nevertheless, I have already shared this link that I'm asking the participants to access, and it will take them to a website that I will go through with you. Just to say here that the game itself is actually under the SMHI with the co-developers of the game being Luis Crossmore, Carolina Cantone, Cristiana Fotiadu, and myself. And there's been a publication at the Bulletin of the American Meteorological Society. The publication was actually this year, with the analysis of close to 300 feedbacks after some filtering of the feedbacks. Yeah, we had a sample of 300 users, and we analyzed it, and we presented results of these thresholds for forecasting reliability and uncertainty thresholds. And also, it's not only from feedback from the hydropower sector, but also from all the other sectors like energy in general, agriculture, water resources management, and so on. And of course, we have to acknowledge the Hydrological and Sample Prediction and Experiment Scientific Initiative. So the game can be found also under the HEPEX link, and the project that was actually funding the implementation of the game and running of the game is actually the Clara Horizon 2020. And here is actually where you can find the game under the HEPEX website, where we are providing also some more information of the game, the objectives, and so on. And if you want to play the game with your colleagues, you can actually download, or you can do that online through your desktop, or you can have your mobile. There's a mobile version of it, or you can download the slides and the worksheets, so you could play the game in a paper form. But nevertheless, if you do that, please let us know, because we are collecting these answers and we are analyzing these answers. So somehow get in touch with us if you're about to play the game, and yeah, we could be aware. So if we have to analyze, we could do that in a quite straightforward way. So with that, I stop with this simple sort of briefing. And I'm just I will take you through the instructions of how to play the game. Yes, so I hope you have all accessed the website that looks like that here. We will go through that together, and nevertheless, I will ask for our champion from our participants. I would like to have somebody, at least in the first round, to tell us what she or he did in terms of decision making. So if you kindly want to volunteer, please do so. Good. So the instructions. So we have the lake here, which we call Bottiglietta, and your role as a player is that you have been appointed as a water manager for this lake, and in this lake, it is actually a reservoir that is used for providing drinking water to the thirsty town. And since you are the manager, you have to provide water to the thirsty town. And we need to provide water in the summer months. So these are the months of June, July, August. And to do so, we need to ensure that these months will have at least 60 millions of cubic meters of water. Otherwise, we are in a critical situation. We are in of providing water. So what we're going to do now is that we're going to have different forecasts initialized in the months of March, April, and May. And these forecasts are always going to tell us what is going to be the capacity of water in the reservoir on the 1st of June. And we will have to have at least 60 millions of cubic meters. This is the objective. Good. And you have, as decision making, you have 4 different options for making this decision on 1st of June. depending on when you will have the forecast as mentioned on March, April, and May, and you will have these 4 decisions. So you could either do nothing, if you expect that your reservoir will reach this threshold of 60 million cubic meters on the 1st of June. You could actually sell the surplus water. So if the forecast tells that you are expecting to have a reservoir capacity of water, volume capacity of 100 million cubic meters, so you could actually sell the surplus for other type of uses. And if you do not expect to ensure this minimum threshold of 60 million of cubic meters in your reservoir, then you will have to contact your neighbors that they can provide you actually with that water, because the thirsty town is actually thirsty. There's a 4th option there, which is for you to wait and see, which means that the forecasted information is not adequate enough for you to take a decision, and therefore you wish to wait until the next forecast comes out. So for instance, if the forecast is actually initialized in March and there's quite large of there's not much of reliability, or the forecasts are quite uncertain, then for you can say, I will wait and see. I don't have to take a decision now. I will wait and see for the next model run. So we could go then in the forecast initialized in April, which it's in theory supposed to be more reliable because we are getting closer to the actual date of 1st of June, and then you could make your decision in April, or you could actually wait for last minute, let's say a month in advance, which is the forecast initialized in May, and then based on that you can make your decisions. Please note here that the wait and see and the do nothing might have the same impact, like you are not selling water or you are not contacting your neighbors. But in terms of us as scientists analyzing the data, the responses, I mean, it makes a big difference, because the wait and see implies that the forecasts are not reliable or they're quite uncertain, and therefore you are waiting for the next model run, while the do nothing implies that you are certain that this status will happen into the future, and therefore I don't have to do nothing. So it indicates higher confidence from your decision-making perspective. So again, so you will receive probabilistic forecasts. Here we're not talking about communicating one value for the future, but we are communicating probabilistic forecasts. And for instance, in PrimeWater, we are communicating 51 ensample members, and this is the case of the forecast that we have here also. So the forecasts are issued on the 1st of March, 1st of April, and 1st of May, together also with their reliability. And then depending on, in all the cases, in all the initialization dates, you would have to make this decision for the 1st of June. But as you are here in the 1st of May, you can see that you have a month in advance to make this decision. So the closer you are in the 1st of June, in theory, the more reliable the forecasts are going to be. While if you make the decision on 1st of April, that means that you are already, the impact is going to be 3 months into the future. And then if you make it on the 1st of March, the impact is also much longer. Yes, and this is how the game is going to look like. So you have an observation here, which is the observation of the status of March. You have March, April, May, and this is June. So the model is initialized in that case in March. This is your observation, and then the forecast tells you that this is going to be the status on the 1st of June. And these are probabilistic forecasts, as I mentioned, and therefore we are having a box plot. And yes, so this is the observation, and these are the probabilistic forecasts. And what is below, behind, as an area is actually the climatology. And what climatology means is the past historical records. So we can understand that depending on the historical records, if these forecasts are actually extremes or not. Now, for those that they are not aware what a box plot is simply a graphical illustration of different percentiles, like different probability ranges. So this part of the box plot is actually representing 25% of the probability. This part of the box plot represents 50% of the probability, and this part of the box plot represents the remaining 25% of the probability. So in principle, this is the minimum of the ensamples, this is the maximum of the ensamples, and this here is actually the median of the ensamples. Now, in addition, you will also get in the game. I just forgot to mention that there are two thresholds here. The first one is the 60, which is the minimum threshold, the 60 million of cubic meters. So if the forecasts go below this threshold, that means that you have to contact the neighbors, while this threshold here is actually the 100 million cubic meters. And if the forecasts go above this threshold, then you will have to, you could sell the surplus and you can make a profit. In all the cases, you want to ensure something that is here. If you have to do nothing in order for you to provide the water to the thirsty town. And in addition to that, you will get a graph that looks like that, and this is the reliability. So here it says that 60% of the time is actually the forecasts were correct. So yeah, if the reliability is 0%, that means that the a posteriori observation is never in the forecast range, so you are never correct. And if it is 100%, that is that you are always in the forecast range. So we want the forecast to be as reliable as possible, of course. Yes, and it's exactly what I mentioned there. So again, this is more like a repetition. If you judge that the forecast information is not adequate to take a decision, you can choose to wait and see. And in that case, if it is above the 100 millions of cubic meters, you can sell the surplus water. If it is below the 60 million cubic meters, you have to contact the neighbors. And if you are within that range, you can do nothing. And now there are some game rules actually here, because yeah, what you will be given is actually 50,000 tokens. We do not want to put a currency there, but you're going to have the tokens. So if you're contacting the neighbor for providing you with water, then you will have to pay because somebody else is providing you with water. Now, the sooner you provide, the sooner you contact the neighbor, the less money you have to pay because they have to get prepared and they're getting prepared in advance. So if you contact them on the 1st of March, then you have to pay 1,000 tokens. If you contact them on the 1st of April, then you will pay 2,000 tokens. And if you contact them at the very last minute, which is actually 1st of May, then you have to pay 5,000 tokens. Now, in the case that you are selling the surplus water, and this is the case where your forecast tells you that you have more than 100 million cubic meters of water, then you are actually gaining. So again, if you are doing that well in advance, which is 1st of March, then you are gaining 6,000 tokens. If you do that on the 1st of April, then you are gaining 4,000 tokens. And if you do that on the 1st of May, then you are gaining only 2,000 tokens. But there's a very big penalty here, which is the penalty that that you made a decision, and then at the end of the day, you did not provide water to the thirsty town. So there is a fine with that, and this fine is quite high, and this is 10,000 tokens. So you always have to provide water to the thirsty town. Now, if there's another type of fine here, which is the fact that if you sold surplus water in the months of March until May, but your reservoir did not reach these 100 millions of cubic meters on the 1st of June, which means that you cannot sell the surplus, but you have promised to sell the surplus, then you have to pay 12,000 tokens. And this is because we have 10,000 for not being able to provide water to the thirsty town, and then 2,000 additional tokens for the loss in your reputation, because you have to be a good manager at the end. So soon we're going to start the game, and you have some specific responsibilities to ensure always the 60 million of cubic meters in the reservoir. And then at the end, there's going to be a value with your budget, like your remaining tokens. So the winner of the game, and I hope we will find a winner today, is that you always have to provide water to the thirsty town, and among those that provide water to the thirsty town, then it is the person that has the largest budget. And we're going to have actually 2 rounds. The first round is that we're going to have 5 years in the first round, and then you will receive an independent set of forecasts, and you will make your decisions. Then in the round 2, then you can actually select of 2 different improved forecasting systems. So if you do not want to pay an advanced service, an enhanced service, then you select the default. And then if there is a silver subscription and a golden subscription, and as you move to the silver and the golden, then the forecasts are actually improved. So you have to pay for an improved service, but then your decisions are going to be more reliable and less uncertain. So I think that now I will stop sharing this sheet, and we will go straight to the game. And I cannot see any of you. So I hope you have accessed this web page. Again, Samuela has put the link in the chat. So just click the link, and then from there you just select the desktop, because we're going to play the game in our desktop. And I press desktop there. Good. And again, you will find the instructions that I have already mentioned so far, so you can go straight to play the game. And I want to give you 2 minutes for you to fill in these preliminary questions. You just have to click your professional background. If you're a hydrologist, climatologist, meteorologist, or you're working with economy or other things, the sector that you are coming from, and I think most of the people here come from the energy sector, your role in the company, if you're a forecaster, decision maker, trader, researcher, consultant, or other, and also the years of your experience. And if you want, you can also put the country where you're coming from. If you have played the game in the past, please tick this option there so that we know that you already have some experience with the game. And what I'm doing here is I'm zooming in a little bit more. So if you want to see what I'm doing, I'm actually a hydrologist. I work with different sectors, but today I will put energy sector there. I'm actually a researcher, and I have years of experience. I think now I'm close to that. This many years of experience. My country is actually Sweden at the moment, and I have played the game in the past. So these are my yes, these are my selections, and I press next. And I hope you have done that. I will give you another 30 seconds. Yes, since I cannot see who has done it or not. In the meantime, if possible, I could ask somebody to volunteer just to share experience only on the first year of the first round. So it's going to be very simple. And if somebody is willing to become the volunteer, thank you.
Hi, I'm Aaron Jordan. I'm playing from IWA. I'm from IWA and I'm playing the game.
Okay.
I'm currently in round 2, but for round 1, the first year, I actually just did not do anything for the first 3 months.
Mm-hmm.
I did nothing, and I came out with 105 million cubic meters in June. Of course, my tokens were not touched, but yeah, that's how I did it for the first year, just to see how it was gonna go.
Thank you, Erin. You went quite some steps ahead.
Yes.
but please pause a little bit. Stay with us.
Okay.
I think I would have liked with some people to discuss at least the first year of the first round, and then I will provide some more information.
Oh, okay. Sorry.
It's okay. Nevertheless, I just proceed with that. These are the instructions. Yeah, I just gave you the instructions already. We do not have to focus on that again. If something is unclear, you can tell me, but I will go straight to round 1. Yes, so let's play the game. So this is what you see. We have the current balance here. I have 50,000 tokens, and this is what I see here. So is there somebody that wants to tell us what she or he will do in this round? These are the forecasts. Shall it be wait and see, do nothing, or do you think that the forecasts are good enough to sell the surplus or to contact the neighbors?
Okay, can you hear me?
Yes.
Okay, this is Ikechukwu from Nigeria.
Yes.
I'm
Nice
a chemical engineer.
Ikechukwu.
Yes, I'm a chemical engineer, and I work as a scientific officer, water analyst in Anambra State, Nigeria.
Thank you.
Okay, I played the first game. Yeah.
So what would you select here for this one?
I did the first one. I selected wait and see.
Wait and see.
Then that's
okay,
on the first month. On the first month. The second month, I saw the surplus.
Sorry, can you a little bit of patience here? So you say that you did wait and see, right? Here.
Yeah, the first month.
Okay, what is your reason behind it?
I looked at the percentage, and it's lower than 25% above the upper limit.
Okay, that's good. So you say that there is quite a lot of percentages that we are between 60 and 100, right?
Yeah.
And this is your driver to say wait and see.
Yes.
Okay, you know that you could have do nothing if you really believe that these forecasts are good enough for giving you a value between those two thresholds?
Yeah, but I just decided to choose wait and see.
Okay, good. Did you take that into account, the reliability that is 70%?
Yes.
Okay, good. Then you chose wait and see, and I will do the same thing here. So I just press wait and see. The others could do the same thing, or they could select whatever they want.
The second month.
And yes, and now we went to the second initialization. So we had the March observation, and now we have the initialization in April, and these are the forecasts. The forecast changed. This is our observation. We can see two things here, that the reliability changed. So from 70%, it went to 80%, simply because we are closer to the forecast horizon that we're interested. And also the forecast changed together with the uncertainty bound.
Yeah.
So I could hear what you have done there and why.
Okay, I saw the surplus.
There you sell a surplus. Okay, why did you sell a surplus for this
There,
year?
based on the reliability and the percentage or the probability is more than 25%.
Okay, good. Actually, the percentage is more than 50%, because this is the median here. And so this part of the box plot should be 50%. And the reliability is indeed 80%. So you sell surplus. And if you sell surplus, because these are the forecasts in April, you're going to get 4,000 token at the end. And hoping that the observations will tell us that we have to sell surplus. So you did this one, and I will also sell the surplus, and I hope the others, they have taken their decision already. So next year, sorry, next month, next initialization.
I still saw the surplus.
Okay, good. Now the reliability increased to 90%. The uncertainty, the probability is quite high also for selling, and also the uncertainty bound was reduced. So I would have also sell the surplus. And let's see, the observations are indeed that in June, we had more than 100 million cubic meters of water, and our decision was correct. So we won with 4,000 tokens. So that was good. And I think, I mean, really thank you for stepping in for that and sharing your experience. And I have somebody, Fatima, sell the surplus from the first initialization month. So she won 6,000. But stay with us, Fatima. You might lose them in the next years. So thank you very much for stepping in and sharing your experience. And now I hope everybody understands how to play the other years. So let's go together. We don't have to share again the experiences. Let's speed up a little bit. So I'm proceeding to the next year, and you can do the same thing. Here I see that these are my observations, that I have quite some probability here, and also my reliability is 70%. So I will be giving everybody something around 10 seconds to, like 5 to 10 seconds to make a decision here. And you will also see, since I'm sharing my screen, you will also see what I'm putting there. But maybe I'm not the best forecaster. Maybe you are better forecasters and decision makers than me. So personally, I would wait and see a little bit more, and there I would have to contact the neighbors, because for me there was high reliability, and also the forecasts are also very certain and with high probability also. So again, I will contact the neighbors. And this is the second year. Good. And I'm done with that. I'm done with the second year. And I see that indeed I have to contact the neighbors. And because I took my decision in April, I just lost 2,000 tokens. So now my budget is 52,000 tokens. Good, I can proceed to next year. And there, what do I decide here? My reliability is 50%. So I have 50% chance. I will wait and see. I'm playing safe, as you can see. Here, I could have done the same. I mean, do nothing or wait and see is going to give me the same outcome at the end of the day. And yeah, I still do not trust this 60% reliability. So I will wait and see one more round. Oh, and now my forecast changed completely. That was interesting because in the initialization in March and April, my forecast, my unreliable forecast, actually, they were saying that on the 1st of June, I will have reservoir volumes that they are in between the thresholds here. But now with the newest, the most updated initialization, there's high probability of having the forecast more than 100 million cubic meters of water. And the reliability is 70%. So maybe here I could actually sell the surplus. But you know that if I sell the surplus and then I'm not reaching this 100 cubic meters, a million cubic meters of water, then I will have to pay 12,000 tokens. So yeah, I can play risky. I can sell the surplus and hope for the best. Good. The best is that indeed the observations show that the volume is actually greater than 100. So I'm actually making a profit here, which is 2,000 tokens, and I have 54 in total. Let me proceed to the next year. Good, very high uncertainty and 50% reliability for initialization in 1st of March. I think I will do wait and see. Then here, I think I will also do wait and see there. I do not trust this forecast. And oh, 90% reliability there, and quite some certainty from the probabilistic forecast that the expected observation will be in between those thresholds. So I will do nothing there. Nice. And the observation for the 1st of June is indeed within the thresholds, and I don't have to do anything. I cannot sell the surplus, and I cannot contact my neighbors. So my tokens remain as they are. So I have 54,000. Maybe another person has more tokens. So that person is winning so far. But let's see the 5th year. So what do I decide here? Very high uncertainty and 50% reliability. I definitely cannot take a decision based on this forecast, so I will have to wait again. My uncertainty now, I think it did not improve. Still, my forecasts are quite uncertain. My reliability increased from 50 to 60. But again, personally, I'm not trusting this forecast. I have to wait and see. I'm going to do wait and see. Nice. So this is a challenge here, because my reliability is 60%. My uncertainty has reduced, and I think I have a little bit more than 25% of my forecast saying that that I will have to contact my neighbors, but still something like 65% of my forecast or 70% of my forecast are within the range of do nothing. So what shall I do? Shall I take into account that 30% of the forecast are good enough for me to make a decision. Let me see. If I fail to deliver water, yeah, I mean, if I contact my neighbors now, I will lose 5,000. If I do nothing, I will lose nothing. But if I fail to contact my neighbors, and that means that I do not deliver water to the thirsty town, then I will lose 10,000 tokens. So it's a matter of probability here for me. I think I will do nothing. So let's see. And I failed actually, because the forecast, okay, 30% is not good enough for me. Okay, and I think it was not also good enough for me. But then the forecast showed that indeed I had to contact the neighbors. So I lost 10,000 tokens there. So my budget is 44,000 tokens. So let's see, that was the round one. So let's see the summary of round one. So far I have ensured water to thirsty town in 4 years out of 5, and this is my balance, 44,000 tokens. So if somebody has 4 years out of 5, sorry, 5 years out of 5, that person is actually among the winners. And if so, I want to see if somebody has 5 years out of 5 that ensure the water. And if you have 5 years out of 5, then the winner of first round should be the person with the highest number of tokens. You can write your score in the chat. So I can give you 15 seconds to do so. It would be nice to, so somebody sells the sell surplus and won. Okay. Okay. Nevertheless, I hope you're still bearing with me, and yeah, I hope we will find the winner. That's the case. Good, and then we can proceed to round 2. So in round 2, we're going to play the same type of game. We will just do the forecast and with the same decisions, but now you can select your subscription. If you want to have a default subscription, that means that you have low reliability. Well, sorry, not very low, but a reliability between 50 and 75%, and also low certainty in your forecast. If you choose, and this is a free actually service, and if you choose to get the silver one, then you have high reliability but still low certainty. And for the silver one, you have to pay 1,000 tokens. And if you choose the golden one, that means you have high certainty in the forecast and high reliability as well. But then you will have to pay 2,000 tokens. So you could see here how the box plot is going to look like if you choose the golden one with low uncertainty, and this is how it's going to be if you go for default or for the silver. The forecasts are going to be highly uncertain, but for the silver one, at least you get high reliability. And this is how much you have to pay. So I think I will go, let's see, maybe I will go for the golden one. So I have to pay 2,000 in this year. And we could speed up with that. This is depending on your subscription, by the way. You will have different type of forecast on your screen. This is something to note. Nevertheless, for me, I chose the golden one, and you see that my reliability is high, and also my forecasts are quite certain. And I think in that case, I can go straight to sell the surplus because I trust the forecast, I trust my service, and also the forecast for above the 100 threshold is also quite high. So maybe I will sell surplus. And here my forecasts are also more certain, and I think that is good. So I will stick to my first decision, and I will sell the surplus of the water. And then the forecast for May, they are super certain. I stick to my decision. It's an easy decision for me, and I'm selling the surplus. And my decision from even from March were correct. I mean, I have surplus in my system, so I can make a profit. So now I increased my tokens by 6,000, and this is very good. And I can proceed to the next year. And again, in the next year, again, I can go with another type of subscription, and I can stick to the goal that I had decided at first in the first year, or I could go for silver all default. Let me be. I'm a little bit curious, so I will go in this round. I will go for the default and see how things are done. So my reliability is between 50 and 75%. So I'm not super happy with that, nevertheless. And also, you can see my forecasts are very much uncertain. So, I mean, I cannot make a decision, a good decision here with this type of default subscription. So I will do wait and see. Next round, again, I'm not super happy with this forecast. I will do wait and see. And yeah, I see that in May, the observation was exceeding my climatology, but my forecasts are still within the ranges of 60 and 100 million cubic meters. I think I will do nothing, and I hope that this year was not an extreme year, and my forecasts were correct. Let's see. Oh, I did do nothing, and yes. So that was there. So that was not a good one. So anyway, I proceed to the next year, and I can make my decision there. Maybe I will go for silver this time. Let's see. So the silver means that I have high reliability, but also not high certainty. And I can see it here. So yeah, my forecasts are quite uncertain. So I will wait and see here. I think I will, for this initialization, I will wait and see again. Oh, and this is a little bit challenging. I think I would interpret this as yeah, quite some signal. So maybe I will do nothing for this one. Yeah, because my observation in May was still within the range, and my forecasts are not. I mean, there's high probability of being within the range, so I will trust this one. So let's see. I will do nothing. Oh, and again, the observations are exceeding the 100 million of cubic meters. So I'm losing all the time. I'm not a good forecaster apparently. So let me do gold this year, and let's hope for the best. There, maybe it's a good opportunity for me to do something with my balance. I think, yeah, my reliability is high, and And also I have 50% probability that the forecast will be below the 60 million cubic meters. So maybe I will contact the neighbors with this forecast already. Next year, oh, these things changed. So I think now I will do wait and see. And here again, the forecast changed. So we are talking about a kind of like unstable year with the forecast changing depending on the initialization month. So, but here I trust I have high reliability and high probability there. So I will contact the neighbors. Good, and my decision was correct. So since I contacted the neighbors from the 1st of March already, I'm losing only 1,000 tokens. And this is good. And let me proceed to the final year. I think I was satisfied with the golden subscription. And due to that, I will take the golden again. And good. So what do I see here? I could sell the surplus, but also there's some probability that I have to be within the range. So maybe in that case, I will wait and see. Oh, but now there is 50% of my probability that is going to exceed this upper threshold. I could sell surplus here already now, and maybe I will do that. I will play risky. And I think now with the new initialization, I'm much more confident. So I could continue, I could stick to my decision, and I will sell the surplus again. So let's do that in the final year. And my decision was correct. So I had a profit of 4,000 tokens. So that's good. My current balance is 53,000 tokens. But as you can see, I did not secure water in the first round. So I'm not among the winners, and I have these 53,000 tokens. So that was the end of the game, actually, and we still have 5 minutes for that. Good. Yes, Kyriakos there ensured 4 years out of 5 with 36,000 tokens, and yeah, and I had to overspend the golden subscriptions. But this is very interesting because each of us are taking different decisions depending on the forecast. And I think now it's actually the end of the game. So so far, yeah, for the round 2, again, Kyriakos secured 4 years out of 5. And that on overhead, yeah, overspent the golden subscriptions. Okay, maybe between the two of us, Kyriakos, I'm the winner, but maybe there are other winners from the participants. As I said, that was the end of the game, and we have 4 minutes. And what I would have liked you to do is to complete this small survey. It is a survey of how useful did you find the following information in your decision making, like with regard to the reliability, to the forecast range, and also to the minimum levels of reliability for you to make the right decision, and the minimum levels of confidence for you to make the right decision. And when, from which month were you willing to make the decision? For the 1st of June, if you had if your decision criteria changed during the game, and what did you think about the silver membership, and what did you think about the golden membership? And if you did not use the silver or the golden membership, then you can do not applicable, not applicable. And of course, you could do you could write some comments there, kind of like feedback to us in general. So I leave you for 3 minutes for you to fill in this this form, and yes, then I will pass the floor to Apostolis for the wrapping up. And how did you find the silver membership? I think it was acceptable when I used it. And how did you find the golden membership? I think it was very worthy to me. Whenever I used it, I ended up to good forecast. Comments. Yes, I don't have many comments, I think. I've played the game. And then it is submit, and we have collected your input there. So 1 minute until the end. I hope you you enjoyed the game. You learned a little bit about the forecast certainty and the forecast reliability. Feel free to play the game and with your colleagues. But again, if you're, I mean, I would appreciate if you tell us if you do so that we know that who you are and when you played the game and so on. And yes, I will stop sharing my screen. Thank you very much. And the floor is back to you, Samuela and Apostolis. Thank you.
Thank you, Ilias, and thank you to everyone. As Ilias was saying, do keep playing the game. I'll leave the floor to Apostolis for some concluding remarks. Thank you.
Thank you, Samuela. It was nice. It was a nice touch playing this game. I hope everybody enjoyed that. But at the same time, was also very serious because it can reveal a lot of dimensions of decision making. But I'll come back to that. For me, it was really nice having this this presentation and discussion following after on this session on this sector, because it's a very let's say related associated sector to the water cycle. Is part of the water cycle. Hydropower is part of the water cycle, and therefore water availability has a key role to play. So that has been clear for all the presentations. And again, there observations and advanced intelligent solutions seem to have also a strong, let's say, role to assist in decision making. One thing that is really, I believe, important and seems to become clear is that water power sector is a regulated sector. So policy context has a significant importance on how this sector operates. Within that context, there were really nice, let's say, suggestions and challenges presented by Christina on the areas where there is still room for new technologies to unleash, let's say, the possibilities of the sector. So flexibility in operations and digitalization become really important, more and more, let's say, pertinent to the sector. So this is a very, let's say, an area where observations and forecasting services can be mapped, among other things. So these are two very solid challenges that the technologies that PrimeWater is dealing with are associated with the sector. And well, another part was very important. It had to do with the reporting requirements and the challenges around climate change, as become evident from discussion. And I think there and the complex and the nexus and the complex nexus that is behind that between energy, water, ecology, or even food. In terms of water, irrigation water, and agricultural water, are critical. And there is also where water quality and the ecological aspects can also can be introduced alongside with the water availability issues. So in that sense, and this is more or less also the connection that I can identify when it comes to the hydrological perspective towards hydropower industry. And I'm going back to the final session, which was really interesting. And I think from the examples also that I've seen in the chat on how different, let's say, players scored in that game, I think another interesting aspect that very, very quickly appears here is the importance, beside all the other and the policy context, the importance of the behavioral patterns of water managers and their perspective of risk towards water availability, which is a very important thing. Water sector is a very conservative and risk-averse water sector. And I think this is a very interesting point also that seems to also appear from these very, very quick responses and reflections to this from this game. So from my side, I think those were the points that I've picked up for just concluding the session. I'd like to thank all the speakers and all the participants, the attendees of this session, of this workshop. I think it was a very interesting session. There is going to be a follow-up from our side, an IWS side. We will let you know on the consolidated, let's say, outcomes of all these discussions that are taking place and have been taking place throughout this week. And also, I'd like to just to mention that this discussion is an ongoing discussion. IWA has provided for a platform that service purveyors in those technological solutions that are related to Earth observations can meet and discuss with actual water professionals. IWA has set up a working group under her auspices that deals with this particular thing, managing the actual water sector needs from all the different sectors with the Earth observation technological possibilities. And the last thing is that, and I think you can see in your screens, a final slide, you will be contacted afterwards, and you would like to have also your view on those and your contribution in this particular survey. This is a tool that has been produced by specialists, behavioral economics, economists that are part of our team, trying to analyze how decisions are taken towards Earth observation technologies from the point of view of the user of those technologies. So it is a very, very useful and powerful tool for analyzing decision attributes and barriers. We would really appreciate having your feedback on that. So you will be sent an invitation to fill in the survey. Please take a few minutes to provide this service. These responses are much appreciated. So that's from my side. Thank you all. Samuela, back to you.
Thank you, Apostolis. And I also would like just to mention that for everyone who will complete the survey, there will also be the possibility to receive a 10% discount code on the membership of IWA. But we hope you will complete the survey to help us with the PrimeWater project. So I think that's it also on my side. Once again, I would like to thank you, to thank all of you for attending, the speakers, the Ilias for this really nice game session. And I hope to see you all tomorrow. We have our final session on the amenity recreation and aquaculture. I put the link in the chat to register. We will start later. We will start at 1 GMT time. So hope to see you all there. So thank you, and have a nice rest of the day. Bye-bye.
Thank you. And many thanks, Samuela, Apostolis, and Christina.
Thank you. Yes.
Likewise, thank you, everyone.